Okay, let's get started. So where did we stop last week? So we started looking at probabilistic generative models, right? And so we spent a lot of time with GDA, which is when your input features are continuous, right? Like, so can someone tell me the two main assumptions that we made to derive the GDA? Yeah.
The probabilities are Gaussians and all classes have the same covariance matrix.
So which probabilities are Gaussian?
So the x slash the class of
So the class conditional density is Gaussian, right? And all the classes share the covariance matrix for the class conditional density, right? So that was the those are the two assumptions that we had for deriving GDA, and eventually we relaxed the sharing of covariance matrices assumption, right? Like, so that's when you arrive at QDA, right? Like, so now what can you tell about the decision boundary of GDA and QDA? Anyone? Yeah.
for GDA is linear and for GDA is not.
Yeah, so GDA has linear decision boundary and QDA doesn't. Right. So because you don't share the covariance matrix, like you'll have some x squared terms coming up, and that will lead to a quadratic decision boundary. Okay, so then towards the end, like, so we talked about how Gaussian assumption is okay when you have continuous features, like and like when you have discrete features. We started talking about making a Bernoulli assumption instead of Gaussian assumption, especially when you have discrete binary features, right? So when you have binary features, as you can see here, then each feature has either 0 or 1. And if you have two features, then to model the probability distribution of two discrete features, then you need to somehow learn this joint distribution table, right? Which has 2 power 2 entries. So in general, like, so for m features, you need to learn 2 power m minus 1 parameters. Right? So this just gets to very large number, like very quickly, right? So for example, even if you have just 100 features, which is not a lot of features, right? Like, so then you already have 2 power 100 parameters to learn, and you don't have that much data, like, to learn, right? Like, so this is exactly when the naive-Bayes assumption is extremely useful. Like, so when you have discrete features, you will rarely see people modeling the joint distribution table. Like, so people typically make some assumptions to reduce table size, right? Like, so the strongest assumption that you could make is the naive-Bayes assumption. So which basically says that, okay, I'm going to model P of x given CK by product of individual features densities, right? Like, so P of x given CK is like modeled as product of I is equal to 1 to m P of xi given CK. So now each of this is a single feature, a single discrete binary feature you're modeling. So how many parameters do you need to model a single binary feature if it is well-known? So what are the parameters of well-known? Yeah. 0, 1. So what are the like if you want to
The probability of the success.
Yeah, the probability of success. There's only one parameter for Bernoulli, right? Like, so which is mu in this equation, right? Like, so if you're modeling each of xi given ck as a Bernoulli, then the parameter is going to be mu ki, which is basically the probability that xi is equal to 1 given the class. Is that clear? Yeah.
I have a question regarding the P of xy knowing ck. Does it like I can't really see it in a practical context, because P of ck knowing x, I can see it as, okay, we have this observation and we want to guess its class. With P of x knowing ck, do we just want to guess the x directly?
You're okay. That's a good point. So what is probably more useful in practice is P of ck given x.
Yeah.
Right. But the whole idea for all this family of like generative models is to first model P of x given ck, which you can view as, oh, how would the distribution of data look for this particular class, right? And you do this for every class. Then you use base rule to reverse these probabilities. So you're going to get P of CK given X, right? So somehow we are making this assumption here that modeling the distribution for each class is either easy or like useful, right? Like, so like intuitively, if you think about it, right? Let's say we want to model, like let's say you have a problem where you have one of classes, like which is birds, like objects, etc. Right? So what we are doing here is like we are trying to model how would, for example, the cat distribution look like. So that is P of xi given ck is equal to cat, right? And then you're going to model P of xi given ck is equal to dog, for example, right? Like so this way you're modeling the distribution of data for a particular class. So then you reverse this using the base rule. Is that clear? Any other question? Okay, so mu ki is probability of xi is equal to 1 given ck. Now, if you want to learn P of x given ck, right? And so which is what you're trying to approximate, right? So we're going to use the base rule and represent this as a product of I is equal to 1 to n individual class conditional like density feature, like density feature, right? Like, so which is mu ki if xi is equal to 1, then 1 minus mu ki when xi is 0, right? So this is just a compact notation for the probability. Okay, so now essentially by making this naive-Bayes assumption, like so we have reduced the number of parameters from 2 power m minus 1 to m, which is a significant reduction, right? Like so from exponential number of parameters, like now we need only m parameters. Is it there? Any questions so far? Okay. So now we will talk about how to learn these parameters. Okay. To the lecture 6. So we are continuing our discussion on Bernoulli naive-Bayes. So for Gaussian discriminant analysis, like what was our objective function? What was our objective function for learning the parameters in GDE?
Likelihood.
Sorry?
The likelihood of the parameters.
So likelihood of the data,
The,
right? Like so we looked at the likelihood of the training set, right? Like and to be more specific, the log likelihood of the training set. And we were trying to maximize the log likelihood of the training set, right? Like so we're going to do the same for Bernoulli naive-Bayes as well. Like so first let's define our likelihood. So the likelihood here is given by the probability of the entire data. Okay, so given mu1, mu2, and 5, which is given by product of n is equal to 1 to capital N. Okay, it's going to be pi times product of I is equal to 1 to capital M mu 1i x x and I. Okay, 1 minus mu 1i 1 minus xi and the whole power tn times 1 minus pi times product of I is equal to 1 to capital M mu 2i xi of n 1 minus mu 2i 1 minus xi of n the whole 1 minus t. Okay, it looks complicated, but what you're okay. Also using pi as a parameter is a bad idea. So if I change it on this part, I'm gonna make mistakes in the derivation. So let's keep it. So this phi is not the product. Okay, so this is just a probability for class one. Okay. If it's class one, the probability is p. If it has zeros, the probability is 1 minus p. Okay. So this phi is the product. Okay, so just to differentiate them. Okay. Okay, so just to differentiate them, I'm gonna make the parameter. Okay, so if it is class one, then the product probability is 5. So then you have for each feature, like what is the probability of that feature, right? So this whole thing is for Tn. So whenever Tn is 1, this is going to be activated and this is going to be 0. When Tn is 0, the first thing is like the whole thing becomes 1. So the second one is activating, which is basically the probability of class 2 followed by the probability of features. Is it clear? Okay, so this looks too big. So I'm gonna put this whole thing as x and this whole thing as y. Okay, and take a log. So the log probability of the data set given mu1, mu2 pi, okay, is basically summation I is equal to 1 to capital N. Okay, so Tn ln x plus 1 minus Tn times ln y. Okay, so I have just taken the log so that the product becomes summation. Okay. Okay, so now let's try to find the parameters, right? Like so first I'm going to start with dou ln p of b divided by dou mu 1i. So what is mu 1i? So mu 1i is mu 1 is basically the first class. Okay, when it's class 1. So what is the probability that the ith feature is on for class 1? So that is mu 1i. Okay, so once we do it for mu 1i, like I think the derivation is same for mu 2i as well. Okay, so this is going to be dou by dou mu 1i, okay, of, let's go back. Okay, so mu 1i exists only in this term, right? So the second term doesn't have mu 1i, so the whole thing in a differentiate is going to become 0. So this is log 80. So this whole thing will become 0. Again, this is also log 80. So this pi will also become 0. So the only thing that you should differentiate is just this term, right? So I can write this as summation n is equal to 1 to capital N Tn ln mu 1i xin 1 minus mu 1i 1 minus xi. Yeah, that's it. The rest all becomes 0. Okay, so this can be written as dou by dou mu 1i of summation n is equal to 1 to capital N Tn, okay, xin ln mu 1i ln a power b is just b log a, okay, plus t of n 1 minus xin times ln 1 minus mu 1i. Okay, so now I'm going to differentiate this and set it to 0. So what would happen? So summation n is equal to 1 to capital N Tn xin 1 by mu 1I plus Tn 1 minus xi n. Okay, when you differentiate ln 1 minus mu, you're going to get minus 1 by 1 minus mu, right? So let me put the minus here. The minus 1 by 1 minus mu 1I is equal to 0. Is that right? So this I can write as summation n is equal to 1 to capital N. Okay. So Tn xin into 1 minus mu 1I minus Tn into 1 minus xin into mu 1I is equal to 0. Okay, I'll just get the things to the other side and the denominator goes to the right, becomes 0. Okay, so let me copy this to the next line. Okay, so this I can write as summation n is equal to 1 to capital N. Let's simplify this. So Tn xin minus Tn xin mu 1I minus Tn mu 1I plus Tn xin mu 1I is equal to 0. You can cancel these two things. So this becomes summation n is equal to 1 to capital N. Tn mu 1I is equal to summation n is equal to 1 to capital N Tn xin. Right? And we are looking for mu 1I, right? So mu 1I is given by summation n is equal to 1 to capital N Tn xin divided by summation n is equal to 1 to capital N Tn. Okay. So can someone tell me intuitively what this fraction means? So what does this mean? You have n examples in total, right? So what is mu 1I?
Weighted average data points of the class of everything.
Sorry, can you repeat?
Weighted average from the data points the class we are looking.
Is it weighted average?
It's not weighted.
So x is binary. So this xi is a binary feature, right? So this is a binary feature, and because we are in mu 1I, right? It's class 1. So whenever it is class 1, so the denominator is just counting the number of times it was class 1, right? And the numerator is counting the number of times in class 1 xi was 1. So in some sense, this is just simple frequency of xi being 1 for class 1. Right? Like, so let's say there are 100 examples in class 1. For 20 out of 100 examples, xi was 1. Then this is saying that the probability of this ith feature being 1 for class 1 is just 20 by 100. So even though it looks complicated, when you implement this, it's simple counting and setting up mu1i directly. Is that clear? So intuitively, what this means is basically mu1i is equal to the number of examples where xi is equal to 1 and t is equal to 1 divided by number of examples where t is equal to 1. Is that clear? Similarly, mu2i is, again, I'm directly writing this. If you want, you can derive it. Number of examples where xi is equal to 1 and t is equal to 0 divided by number of examples where t is equal to 0. Is that clear? Any question? Okay, so now let's look at an example application for Naybase. Okay, so we're going to do text classification. Okay, where the idea is given some document, which is a bunch of words, right? Like, so I'll give you a document, and I want you to classify this into among a bunch of K topics. Okay, for example, sports, entertainment, like politics, etc. Okay, maybe you should give us a news article, like we are interested in classifying this article into either sports or politics or entertainment or science, etc. Okay, so this is the task. Now, I think in the past we have seen like simple classification problems, like where you were given a bunch of features and you are interested in classifying the input X, right? So here your input is a document. So how can we represent documents? So what kind of features that we could use for representing documents? So one of the problems with documents is they are going to be of variable length, right? Like it's not like you have 100 features that you are fitting a model which takes 100 dimensional vector and outputs, if there are 10 classes, like a 10 dimensional probability distribution, right? We're not doing that. So in this case, for example, let's say I have a document. It says, so today is Thursday. Okay. And there's no class tomorrow. Okay. This is my document. Now, how do I represent this document as a vector? Any thoughts? Yeah.
We do like the one-hot encoding for if a certain word appears.
Okay, so you could do a one-part encoding if a certain word appears, right? So that's the simplest possible representation for this document. Like, so to do that, the first thing is you need to know all the possible words that could appear, right? Like, so like a simple way to find that is just to come up with a unique list of all the words in your training data. Okay, yeah.
Jump in and a specific word.
Yes. Yeah, you can count too. So let's start with the simple representation, then we will generalize. So the idea here is to first come up with a vocabulary of all words that are possible, right? Like let's say we have 1,000 such words, just as an example, right? So then you have 1,000 words that are possible. Okay. Now, the simplest representation one could think of is called binary bag of words representation, like which is basically you're going to see which word appears here and put a 1 for the corresponding place in the vocabulary. Okay, so for example, like let's say today is here, right? So then you put a 1 here. Let's say is somewhere here, you're going to put a 1. Is appeared twice. However, I'm still putting 1, like because we are using binary features now, right? And maybe there's a Thursday somewhere here. I'll put a 1. Okay, so for every word that appears in the document, you put a 1, and for the rest, you fill 0. Is it clear? So now the advantage of this representation is like, I can give you different documents with different lists. For the classification model, the input is always 1,000. There are fixed number of features 1,000, right? So now there was a second suggestion, which is instead of using binary bag of words, you could also use frequency-based bag of words, like where like instead of putting 1 for today, sorry, no, is, right? I'll put 2 for is because is appeared twice, right? You could actually have the number of times each of these words appeared in the document if you want to somehow capture this information as well, right? So you could use either of these representations. It doesn't matter. But because we are learning Bernoulli database, it can only use binary features, right? Like, so we're going to use the binary bag of word representation. Yeah.
Is it possible for the word to exist in the document, but not in the bag of words?
That's a good question. So if you're constructing your vocabulary using the training set, okay, so then every word that is in the training set is going to be in the vocabulary. However, there's no guarantee that words in the validation set or test set is going to be same set as the training set, right? So which means that you could see a document where you have a word which doesn't exist in the vocabulary. So what can you do then? Yeah. You could add an unknown word, okay, yeah.
Find the closest word.
So if you can find the closest word, yeah. So these are all valid heuristics. Any other thoughts? Yeah.
I know it may be cheating, but like add all of the new words from the testing set into the vocabulary.
But what's the point though? Like, so if you're adding this later, the probability, the mu for that word is going to be 0 anyways, right? Because you never saw that in the training set, right? Like, so the probability of that word existing is actually 0 based on the values, right? So there's no point in adding it later. I mean, you cannot add it before. Even if you're adding it before, it's cheating, but that's not helping you, right? So what else can we do? Well, a simple heuristic that you will often find people doing is just to ignore that word. So if you see a word that is not in your vocabulary, you just ignore it, then you are still with a thousand dimensional representation. Okay, it's not ideal, but it's fine in most of the situation. Is that clear? Any other question? Okay, so this is good. So now, if I give you a bunch of documents, you should be able to construct the vocabulary and convert all the documents into this thousand dimensional representation, right? So then implement Bernoulli database, right? Oh, by the way, I did not derive the pi in Bernoulli database simply because the derivation is same as we did for Gaussian database. Okay, so when you do pi, if you go back, yeah, when you do pi, the remaining things become 0. So the derivation is exactly same as before. So basically pi is going to be the number of times. So this is okay. So the number of examples with t is equal to 1 divided by total number of examples. So that is pi. Okay. So now let me write p of ck given x as p of x given ck times p of ck, which is basically product of I is equal to 1 to capital M, p of xi given ck times p of ck. Right? Okay. Now here's okay. So given this data sets, you can learn the probabilities, and given a new document, you can do p of ck given x by just using this formula, right? Now, there is a problem in doing document classification this way. Can you think about what could go wrong? Like if I use name base assumption plus base rule, like for binary features.
Well, pour prochaine discussion, the document is on a certain topic, words related to the topic, you can move the document.
We are not following the version. We are assuming we have to say is library, right?
It's an injunction.
Yes, but that's what you can model. Right. Yeah.
There's too many values x, y can take. Because since x, y can be.
So M here is the number of features. And P of xi given ck is basically the probability that the first feature is on given ck.
Okay.
Okay, and they're doing this for all the young features. Like if you have 1,000 words, then you're doing the probability of each word being on given a class multiplied by the probability of a class. Okay, now think about this. Like, so let's say my vocabulary is 10,000 words. Would you see all these 10,000 words in every class distribution? Let's say I have a sports class. Okay. Would you see Apple in sports class? Okay. News articles about sports. Maybe very rarely there could be a mention of an apple, right? But it is very rare. Maybe it's a bad example, but you could think of words. You could actually think of a lot of words that would never appear in sports documents or in politics documents or in entertainment documents, right? So in some sense, this vector that you're creating is going to be a sparse vector. It's sparse, well, partly because you have short documents and you have very large vocabulary, right? It's also sparse because there are certain group of words that would never appear in other classes, right? So this means it's going to be the case that for some classes, xi is going to be 0. For all instances in some class, right? So in that case, mu1i is going to be 0. But when you have 1 0 in a product of 1,000 probabilities, the whole thing becomes 0. Right? So in some sense, all your calculations will become 0 because there are 1,000 or 10,000 words. You will always find 1 or 2 words which has probability of being occurrence being 0 for a particular class, right? So in some sense, all your P of ck given x is going to be 0. So then it's not a useful classifier, right? So how can you fix this problem? Yeah.
You can just give it a very small probability.
You can give a very small probability for each word for a class, which by the way, that makes sense, right? Like, so as I said before, maybe you would never see Apple in 10,000 sports documents. As a rare instance, there might be one document maybe mentioning a sports player eating apple in between, right? Like, so it's a random news article, but you could see it, right? So it's fair to assume that each word has a very small non-zero probability. Yeah.
So we remove it from the vector.
Or
Like the words that are very rare, we just stop considering them at all.
okay, so you could consider removing rare words from the vocabulary, but then there are certain words which are just rare all the time. Okay, but then there are certain words which are just rare for a particular class, right? Like, so then you cannot remove them, right? Like, they might be frequently occurring words in other classes, right? So in that case, I think your idea of like having a very small probability for each word makes sense. Okay, so this is in some sense called smoothing. Okay, in like in the literature. So what we are going to do is, so in this case, like what we are going to do is we are going to make an assumption that each word occur at least once in every class. Okay, so this is just an assumption. Like I'm making, instead of being the count, instead of the count being 0, I'm gonna count to starting from 1 for each word. Okay, so this is called Laplace smoothing. Okay, which basically says, okay, mu1i, right, which was originally the number of examples where xi is equal to 1 and t is equal to 1 divided by number of examples where t is equal to 1, right? So I'm going to assume that this word occurred at least once, even though it doesn't occur in the training set. And I'm going to put a +2 here. Okay, so essentially I'm introducing a bias that when you have not seen any examples, the mu1i is equal to 1 by 2. Right? So I'm introducing a bias here saying, oh, if I, without seeing any training documents, the probability of each feature being 1 is 0.5. Okay, now as you see more and more training documents, let's say this word never occurs. If this word never occurs, the denominator is going to keep growing, right? So first document becomes 3, second document becomes 4, third document becomes 5, right? The denominator is going to keep growing. The numerator is going to be always just 1 if this word never occurs. So for rag words, you will have probability which is like 1 by 10,000 if you have 10,000, 10,002 if you have 10,000 documents. Okay, so you end up with a very small probability, but it is still non-zero, so that your probabilities don't go to 0. Is that clear? Any questions so far? Any question? So for your second assignment, you are not implementing Bell Labs, you're implementing Gaussian Labs. Is that correct? So how many of you have read the second assignment?
Yeah, just the beginning, and then again, we'll show K and then.
So just 2 people? 3, 4, 5? Yeah.
Do you have to then compensate for all of these minuscule languages?
No, not necessarily. So like, because you're just comparing against different classes, like, so this is relative comparison, right? Like it's okay. Like you're making this assumption for all the classes.
Yeah.
So this is okay. Okay, I think you're implementing Gaussian Labs, not discrete Labs. Anyways,
Yeah, we are.
yeah. So anyways, like all these generative models that we have seen last week and this week, it looks like the derivation is complicated. But once you do the derivation, the answer is always intuitive. So when you implement, it all boils down to computing the empirical mean, empirical covariance, or the frequencies. Okay, so which is just counting or averaging, right? And so when you implement this, it should be very easy to implement. Is that clear? Yeah. Any other questions? Okay, so I want to start with discriminative models. Why don't we just take a break? So let's take a 10-minute break.